For the second unit of thermodynamics, in previous lecture we discussed the thermodynamic temperature scale, entropy change for an ideal gas having temperature and volume as variables, entropy change for an ideal gas having pressure and temperature as variables, and entropy change for an ideal gas in isothermal, isobaric and isochoric processes. Today we are going to discuss the entropy change in reversible and irreversible, that is spontaneous processes. Second law of thermodynamics in terms of entropy. Entropy change accompanying change of phase, that is during fusion, vaporization, sublimation and transition. Entropy of mixing of ideal gases and the relationship of entropy with equilibrium. First, we are going to discuss the entropy change in reversible and irreversible processes. Consider isothermal expansion of a gas at external pressure 0, or we can say isothermal expansion of a gas in vacuum. Here the temperature is constant, hence increase in internal energy will be equal to 0, that is delta U to 0. As there is no opposing force, or we can say as external pressure is 0, hence there will be no work done on the gas. Now according to first law of thermodynamics, you know that delta U equal to Q plus W. Here du is equal to 0 and W is also equal to 0. Hence we will get Q is equal to 0. Therefore, no heat will be removed or supplied to the system from the surroundings. Hence, we can say that entropy change of the surroundings will be equal to 0. You also know that entropy is a state function, that is, it depends only on the state of the system of pressure, temperature and volume. If the gas expands from an initial volume of V1 to a final volume of V2 at a constant temperature T, then entropy change of the system will be given by the equation delta S equal to R natural log V2 divided by V1. Therefore, the entropy change of the system and the surroundings taken together will be equal to R natural log V2 divided by V1. As this is the process of expansion, hence V2 will be greater than V1, or we can say that delta S will be positive. Therefore, we can say that entropy increases during isothermal expansion. Now consider the isothermal expansion of a gas reversibly. Here let us take P1 as initial pressure and P2 as final pressure and V1 as initial volume and V2 as final volume, and constant temperature is taken to be equal to T. As the process is reversible and isothermal, the system will remain in equilibrium with surroundings all the time. Therefore, heat given out from the surroundings will also be equal to Q reversible. Hence, the change in entropy for the surroundings will also be equal to Q reversible divided by T. Now, giving appropriate sign for the entropy of system and entropy of surroundings, that is, increase in the entropy of system will be positive and decrease in the entropy of surroundings will be negative. We will get the equation Q reversible divided by T minus Q reversible divided by T, which will be equal to 0. This is the entropy of universe, that is surroundings and system taken together. Therefore, for a reversible process, entropy change of universe, that is entropy change of system plus entropy change of surroundings, will be equal to 0. Hence, we can conclude that a thermodynamically irreversible process is always accompanied by an increase in the entropy of the system and its surroundings taken together, while in a thermodynamically reversible process, the entropy of the system and its surroundings taken together remains unaltered. This generalization constitutes a criteria for distinguishing between reversible and irreversible process. Delta S system plus delta S surrounding will be equal to 0 for reversible process and delta S system plus delta S surrounding will be greater than 0 for irreversible process. Combining the two, we will have delta S system plus delta S surroundings greater than or equal to 0. Here, equal to sign refers to reversible process and greater than sign refers to irreversible process. This conclusion is of great importance because it helps us in deciding whether the process is spontaneous or not, that is, whether the process will take place of its own thermodynamically or not. Since all the processes occurring in the nature are irreversible or spontaneous, we can say that entropy of universe continuously increases, and this is the basis of second law of thermodynamics. The essentials of first law and second law of thermodynamics were thus summed up by Clausius as the energy of universe remains constant and the entropy of the universe tends towards a maximum. Now we are going to discuss entropy change during phase change. When there is a change of state from solid to liquid, liquid to vapor or solid to vapor, that is fusion, vaporization or sublimation, entropy change can be calculated. These changes takes place at constant temperature as the two states remain in equilibrium. Let us discuss entropy of fusion. Let us consider the melting of 1 mole of the substance. It will absorb the heat equal to its molar heat of fusion during melting, and this process will take place at a constant temperature will be equal to its melting point. Therefore, entropy change of fusion will be equal to delta H of fusion divided by temperature of fusion, which is the melting point of the substance taken in Kelvin. Here delta HF is the molar heat of fusion at its melting point Tf and delta SF is the change in entropy of fusion. Now we will discuss entropy change of vaporization. If 1 mole of the substance vaporizes at its boiling point, it will absorb heat equal to molar heat of vaporization at a constant temperature, which will be equal to its boiling point. Therefore, delta SV, which is change in entropy of vaporization, will be equal to delta HV divided by TB. Here delta HV is equal to molar heat of vaporization of the substance and TB will be equal to the boiling point of the substance taken in Kelvin. Now we will discuss the entropy change of transition. When 1 mole of a substance changes to its different allotropic form, then entropy change of transition is equal to delta HT divided by T. Here delta ST is the entropy change of transition, delta HT is the molar heat of transition at its transition temperature, which is given by Tt. This temperature is also taken in Kelvin. Here are few examples to understand the calculation of entropy change of fusion, or we can say entropy change of vaporization also. Calculate the entropy change when 1 mole of ethanol is evaporated at 351 Kelvin. The molar heat of vaporization of ethanol is 39.84 kilojoules per mole. Now you know that delta SV will be equal to delta HV divided by TB, where delta SV is change in entropy of vaporization, delta HV is molar heat of vaporization, and TB is the boiling point of the substance in Kelvin. In the problem, delta HV is given to be equal to 39.84 kilojoules per mole, which will be equal to 39840 joules per mole, and boiling point in Kelvin is given to be equal to 351 Kelvin. Therefore, delta SV will be equal to 39840 divided by 351, which is equal to 113.5 joules per Kelvin per mole. Here is another example in which entropy change of fusion will be used to calculate the temperature at which melting will take place. 30.4 kilojoules is required to melt 1 mole of sodium chloride. The entropy change during melting is 28.4 joules per mole per Kelvin. Calculate the melting point of sodium chloride. Now you know that delta SF is equal to delta HF divided by TF. Here delta SF is entropy change in fusion process, delta HF is molar heat of fusion, and TF is melting point of the substance taken in Kelvin. In this problem, delta SF is given to be equal to 28.4 joules per Kelvin per mole, and delta HF is given 30.4 kilojoules per Kelvin per mole, which will be equal to 30400 joules per Kelvin per mole. On substituting these values, we will get TF equal to 30400 divided by 28.4, which will be equal to 1070.4 Kelvin. Now we will calculate the change in entropy of mixing of two ideal gases. For this, let us consider a system containing two ideal gases A and B separated by a partition. Here, gas A contains the number of moles equal to Na, and gas B contains the number of moles equal to Nb. The volume of gas A is equal to Va, and that of gas B is equal to Vb. These two gases are separated by a partition, but if this partition is removed, these two gases will diffuse randomly and will make a homogeneous mixture. You can see this process in the figure. The two gases has been diffused to make a homogeneous mixture. To calculate the entropy change, let us consider the two separate expansions, that is, the expansion of gas A and that of expansion of gas B. If the initial volume of a gas is V1 and it expands to a final volume of V2 at constant temperature, then entropy change of the gas will be given by delta S equal to Nr natural log V2 divided by V1. Here delta S is increase in entropy, N is total number of moles of the gas, R is universal gas constant, V2 is final volume of the gas, and V1 is initial volume of the gas. Now for the gas A, Va is the initial volume and Va plus Vb will be the final volume. Similarly, for gas B, Vb will be the initial volume and Va plus Vb will be the final volume. Therefore, delta SA will be equal to Na R natural log Va plus Vb divided by Va, and delta Sb will be equal to Nb R natural log Va plus Vb divided by Vb. Here, delta SA is increase in entropy during expansion of gas A, and delta Sb is increase in entropy during the expansion of gas B. Na is the number of moles of gas A and Nb is the number of moles of gas B. So, for the calculation of entropy change during mixing, we can add these two entropy increases. Therefore, delta S mixing will be equal to delta SA plus delta Sb, which will be equal to Na R natural log Va plus Vb divided by Va plus Nb R natural log Va plus Vb divided by Vb. Now, you can recall that for ideal gases, PV is equal to nRT. We can say that volume is directly proportional to number of moles. Therefore, Va upon Va plus Vb can be replaced by Na upon Na plus Nb, and Vb upon Va plus Vb can be replaced by Nb upon Na plus Nb. Putting these values in the equation, we will get delta S mixing will be equal to Na R natural log Na plus Nb divided by Na plus Nb R natural log Na plus Nb divided by Nb. Now, you know that Na upon Na plus Nb will be the mole fraction of the gas in the mixture of two gases, and Nb upon Na plus Nb will be the mole fraction of the gas B in the mixture of two gases A and B. Therefore, taking the inverse of Na plus Nb divided by Na and Na plus Nb divided by Nb and putting in the value, we will get delta S mixing equal to minus Na R natural log Na upon Na plus Nb minus Nb R natural log Nb upon Na plus Nb, which is equal to minus Na R natural log Xa minus Nb R natural log Xb. This we can obtain because natural log of 1 upon x will be equal to minus natural log of x. In this equation, Xa is the mole fraction of the gas A and Xb is the mole fraction of the gas B. Now, if we take R as common in both these entropies, we will get delta S mixing will be equal to minus R multiplied by Na natural log Xa plus Nb natural log Xb. This equation can also be written in the form of mole fraction taking total number of moles outside the bracket. We will get delta S mixing equal to minus Nr multiplied by Xa natural log Xa plus Xb natural log Xb. Here N is total number of moles, that is Na plus Nb. You can note that when the two gases are mixed, their mole fraction will be decreased. Hence, log of a value which is less than 1 will be negative. This will make the value inside the bracket as negative. Therefore, delta S mixing will be positive. Hence, we can say that when two gases mix, the entropy increases. Here is an example to calculate the change in entropy or increase in entropy of mixing of two gases. What is the change in entropy when 0.7 meter cubes of carbon dioxide and 0.3 meter cube of nitrogen, each at 1 bar pressure and 25 degrees Celsius temperature, blend to form a homogeneous mixture at the same condition. Assume these two ideal gases. As there is no change in temperature after mixing, therefore, increase in internal energy will be equal to 0, or we can say that dU will be equal to 0. And you know that dU is equal to TdS minus PdV, and as dU is equal to 0, therefore, we will get TdS is equal to PdV, or we can say that ds is equal to PdV divided by T. You also know that for an ideal gas, PV is equal to nRT. Therefore, we can have the value of P by T, which is equal to nR divided by V. Now, substituting this value of P by T in equation ds is equal to PdV divided by T, we will get ds is equal to nR dV divided by V. And on integrating this equation between the limits V1 and V2, we will get ds is equal to nR natural log V2 divided by V1. As mixing of ideal gases is irreversible process, we can calculate the total entropy change of the system for mixing by considering equivalent reversible processes. First step will be reversible expansion of gas from its initial volume to the final volume of 1 meter cube. Entropy change for this process is given by the equation ds equal to nR natural log V2 divided by V1, where V2 is the final volume, which is 1 meter cube, and V1 will be the initial volume for both the individual gases. The second step will be the mixing of two gases at identical conditions of temperature and of volume equal to 1 meter cube. Since there is no change in thermodynamic conditions in this process, entropy change is 0 for this step. This is so because entropy change is a state function. Now, we will calculate the entropy change for both the individual gases and add them both to get the total entropy change for mixing of two gases. First, we will calculate the entropy change for carbon dioxide. For that, we need the number of moles of carbon dioxide. As you know that PV is equal to nRT, we can say that N will be equal to PV divided by RT, and putting the values of P, V and RT, we will have number of moles of carbon dioxide equal to 10 to the power 5 multiplied by 0.7 divided by R multiplied by 298. Here 10 to the power 5 is the pressure in newtons per meter square, 0.7 is the volume in meter cube, and 298 is the temperature in Kelvin. So, number of moles of carbon dioxide will be equal to 234.9 divided by R. Now, as you know that ds is equal to nR natural log V2 divided by V1, we will get ds is equal to 234.9 divided by R multiplied by R natural log 1 upon 0.7. You will get ds is equal to 234.9 natural log 1 divided by 0.7 equal to 83.78 joules per degree Celsius or joules per Kelvin. Similarly, we can calculate the entropy change for nitrogen also. Now, number of moles of nitrogen will be equal to PV divided by RT. P is 10 to the power 5 newtons per meter square, V is 0.3 meter cube and T is 298 Kelvin. Putting all the values, we will get number of moles of nitrogen equal to 100.7 divided by R. Now, ds will be equal to nR natural log V2 divided by V1. Therefore, ds will be equal to 100.7 divided by R multiplied by our natural log 1 upon 0.3, which we will get 100.7 natural log of 1 divided by 0.3, which is equal to 121.24 joules per degree Celsius or joules per Kelvin. Now, entropy change of mixing for the system, we will have ds mixing equal to 83.78 plus 121.24 equal to 205.02 joules per degree Celsius or joules per Kelvin. Now, we will discuss the relationship of entropy with equilibrium. As we have defined entropy, hence we have a powerful tool to attack on a fundamental problem of physiochemical equilibrium. Any spontaneously occurring change in an isolated system is accompanied by increase in entropy. And by first law of thermodynamics, we know that energy can neither be created nor be destroyed. Hence, the internal energy of an isolated system remains constant. The only way in which such a system can gain or lose energy is by the interaction of the system with its surroundings. But the absence of this interaction is the condition what we mean by isolated system. Thus, in case of isolated system, no work is done and no heat is exchanged between the system and the surroundings. If we restrict the thermodynamic work to pressure volume work, that is work of expansion or work of compression, and exclude all linear and surface effects, then it may be concluded that an isolated system must have a constant volume also. Therefore, an isolated system can be defined as a system with constant energy and constant volume. Hence, we can say that in an isolated system with constant energy and constant volume, any spontaneously occurring change is accompanied by increase in entropy. Now, we know that a system is said to be at equilibrium when it has no further tendency to change its properties. The entropy of an isolated system will increase until no further spontaneous changes can occur. Therefore, a criteria for thermodynamic equilibrium can be summarized as: in a system at constant energy and volume, the entropy is a maximum, or we can say that at constant E and V, S is maximum. If instead of a system at constant energy and volume, we take the system with constant entropy and volume, we can say that the condition of thermodynamic equilibrium is that at constant entropy and volume, the energy of the system must be minimum. Therefore, the drive, or perhaps we can say the drift towards the equilibrium for physicochemical systems is the maximum entropy condition and minimum energy condition. In the end, let us revise what we have discussed today. First, we discussed the entropy change in reversible and irreversible, that is spontaneous processes. Second law of thermodynamics in terms of entropy. Entropy change accompanying change of phase, that is during fusion, vaporization, sublimation and transition. Entropy of mixing of ideal gases and the relationship of entropy with equilibrium. In continuation, in next lecture, we will discuss the physical significance of entropy and characteristics of entropy.